Dear viewers, welcome to the UGC lecture series in biophysics. Today we are going to see how the three-dimensional structures of small molecules can be determined using single crystal X-ray diffraction. So, we have to know what is phase problem, what are direct methods, what are the various steps necessary in determining the three-dimensional structure of molecules, and what are the programs mostly people use in getting the molecular structure. Phase problem already we have seen, direct methods also we have separate episode for that. Our main concern here is to look into the means of determining the three-dimensional structure of molecules using package. Many packages are there, we are going to look into the package written by Professor George Sheldrick from Germany. As we have seen from the previous episodes, the three-dimensional crystallography analysis means for every atom constituting the molecule, we are getting three positions of the atoms, that is called 3 dimensions, for which the molecule has to be crystallized first. When we say crystals in crystallography, single crystal X-ray diffraction, we mean only the sizes of about 0.2 millimeter. Only thing is length should be 0.2 millimeter, breadth should be 0.2 millimeter, and thickness should be 0.2 millimeter. Once you have the crystals ready, then you take it to a diffractometer, measure the diffracted intensities. From the diffracted intensities, we can take the square root and get the structure factor amplitudes. But in order to locate the position of each atom, we have to do a mathematical synthesis called Fourier synthesis, for which the coefficients are not only these structure factor amplitudes available from experiment, but also the phases of the Bragg refractions which are unknown from the experiment, and this non availability of phases from diffracting experiment is called the phase problem in crystallography. Nearly 7 or 8 decades ago, crystal structures have been solved mainly by these mineralogists or geologists for molecules containing very less number of atoms in the unit cell, and most of the times intuition and expertise played major roles in arriving at the molecular structures, as there was not any correct procedures available for solving the phase problem. There is no systematic methods were available. But in 1950s, Professors Hoffman and Karl came out with some drastic assumptions like the electron density should be very positive, and the real crystal with continuous electron density can be assumed to consist of n non-vibrating point atoms. But these assumptions were against the principle of physics, and they were not accepted, because atoms, as per the theory of solid state physics, atoms undergo thermal vibration, and when atoms contain different electrons, how can you consider them as a point atoms? But Hoffman and Karl insisted that based on their assumptions, which is again approximate, they would simply produce a model with tentative coordinates, 3 coordinates of each atom, which can later be subjected to adjustment of positions and thermal factors, which are called technically refinement procedures, then leading to reality. Even then, even though the arguments are convincing, they were against this, and entire global level did not accept this formalism called direct method, which means directly from measured intensities we can get the molecular structure. Of course, they get the structure using some relationships among phases called structure invariance and semi invariance, but not bothered by the severe criticism being faced that time. Karl and Hoffman worked together many formula for solving phase problem in specific phase groups, and also they have written a monograph called Solution of the Phase Problem Part 1, the centrosymmetric crystal, and this was published by the American Crystallography Association in the year 1953. The reason why they took centrosymmetric crystal is that the phase problem in the case of centrosymmetric system can go only 2 values, either 0 or pi, whereas in case of non centrosymmetric, the phases can be anywhere between 0 to 2 pi. These two scientists, Karl and Hoffman, later came out with a formula called tangent formula. The name tangent formula comes because it is a numerator is a form of sine function and denominator is a form of cos function, which is called the tangent formula, and this is the principle of direct methods relating the experimentally known structure factor magnitudes to the desired phases. In 66, Dr. Isabella Kahl, the wife of Professor Jerome Kahl, proved that a dipeptide case can be solved for its three-dimensional structure by using the methods developed by Kahl and Hoffman. Then only the physicists who have been objecting this from the beginning accepted, and they also start writing the program, and the first automated program was released from University of York, England by the team headed by Professor M. M. Wolfson. So, Professor Peter Mine and many people were the co-authors in that. The program name was Multon. Mult means multi-solution. Direct methods does not give you single solution, it is multi-solution. Then tangent formula gives you the phases, refined phases, it is called multi-solution tangent formula. Many scientists all over the world have also contributed in the field of direct methods in different topics, but enormous contribution and continuous contribution have been done only by Professors Kahl and Hoffman. And of course, they have been honored for their contributions. In the year 1985, they share the Nobel Prize in chemistry, and by that time more than 50,000 small molecule structures have been determined. Now, as on date, more than 11.6 small molecular crystal structures have been determined using the methods called direct methods proposed by them. During 76, an Italian scientist, Professor Giacavasso, came out with representation theory. He is from University of Bari, Italy, and this representation theory is a generalized one, and this covers most of the formula derived by Kahl and Hoffman. The difference between the assumptions made by Kahl and Hoffman and Giacavasso is that one team assumed the crystal structure to be fixed. Crystal structure means atomic coordinates to be fixed, and assumed the HKL is known, whereas reciprocal lattice vectors are the random variables, whereas the other team assumed the reciprocal lattice vectors to be fixed, as Miller indices HKL, and consider the atomic coordinates as the random variables. So, if you look at the formula H dot Rj, which is simply Hxj plus Kyj plus Lzj, in which HKL are the Miller indices which can be positive or negative including 0, and Xj, Yj, Zj are the fractional coordinates of every atom j. We want this quantity Hxj plus Kyj plus Lzj should be a random variable as per the derivations of this both the people. You can do this by fixing Xj, Yj, Zj as random variable, automatically this product becomes a random variable, or when you say HKL as random variable, again this product becomes random variable. Ultimately, what we need is H dot Rj should be a random variable. By virtue of the above, the structure factors which involve this quantity themselves will be a random variable, because structure factor depends on HKL and this Xj, Yj, Zj is no. So, structure factors themselves are random variables. For easier mathematics, instead of assuming the normal structure factor corresponding to spherical atomic cloud, Kahl and Hoffman assume point atoms, which means we cannot use the normal structure factor, but there is something known as normalized structure factor E's, which do not vary with respect to the glancing angle theta through sin theta by lambda. This is simply for easier mathematics. At present, more than 99% of small molecular structures are solved by direct methods only, and even though Multon was used initially, later on due to the very short time taken by this program and the success of this, Shell's suite of programs are used global level, and Shell denotes the name of the author, Professor George Sheldrick, and he has two versions, Shell's L, Shell's S. Shell's S means structure determination, Shell's L means least square refinement, which you will see later. Now, the systematic way of overcoming phase problem was provided by Kahl and Hoffman through the equation. So, expectation value of the product E h multiplied by exponent minus 2 pi I h dot r average over h would be simply f j naught divided by sigma 2 power half. Sigma 2 is nothing but summation over square of the atomic scattering factor, summation over f j square, j running from 1 to capital N, total number of atoms in the unit cell. Only at atomic site this map called E map will show non vanishing value, and at other places it will be having 0. So, this E map shows the peaks only at atomic sites. So, that is what non-zero values, and other points non-atomic site it will be 0. Now, in this formalism the unknowns consist of the n phases. Suppose you have n reflections. So, you know the intensities only or structure factors are this only, but phases are unknown. So, n phases are there, and what are other thing? Every atom has 3 coordinates unknown. Suppose n atoms are in the unit cell, 3 n coordinates you have determined. So, total number of unknowns will be this n plus 3 n, right. Now, if we equate the real and imaginary part of the structure factor equation, we have 2 n equations, but usually if you take 500 or 600 reflections, then this 2 n is much larger than n plus 3 n, which means that the phase problem formulated by the above equation is possible, because we have redundant number of equations. The number of equations available exceeds the number of unknowns. Okay. So, that is what I have been telling here. Then Hoffman and Karl introduced 2 types of special relations, phase relationship. One is called structure invariance and another is known as structure semi invariance. Structure invariance means a linear combinations of phases which remain invariant or unchanged when the origin is moved. So, it did not tell you where it is moved, that is all. Whereas, structure semi invariant means a combination of phases which remain invariant or unchanged when the origin is moved within those permitted by space group symmetry. So, here the movement of origin is restricted, here it is general. Okay. So, using these 2 types of phase relationship, they generalize the direct methods formalism, and they also proved that when the origin is shifted, it is only the magnitude of structure factor which remains constant and phase changes. Although single phase changes with shift in origin, there are some special combinations of phases like phi h plus phi k plus phi l, and these phases when h plus k plus l equal to 0, they do not change their value, and these are called structure invariant. So, you should not get confused when I say h plus k plus l. When I say h, it is a reciprocal lattice vector, maybe h 1 k 1 l 1. When I say k, it is another reciprocal lattice vector h 2 k 2 l 2. When I say l, another Bragg reflection h 3 k 3 l 3. But when I say h plus k plus l equal to 0, you have to add all the h parities, add all the k parities, all the l parities, which means that h 1 plus h 2 plus h 3 should be equal to 0. Then your k 1 plus k 2 plus k 3 should be 0, and l 1 plus l 2 plus l 3 should be 0, which means that all these 3 equations satisfy h plus k plus l equal to 0. The structure semi invariants are linear combinations of phases which remain unchanged when the origin is moved to within those permitted by space group symmetry. As per the statement, we understand that depending upon the space groups, the origins are limited. We cannot change the origin arbitrarily. The origin choices are limited. The probabilistic of these relationships, structure invariants, semi invariants, have already been derived by Karl and Hoffman. Then, using these in the tangent formula, the E values corresponding to your point atom structure factors, then during the refinement, they use tangent formula to get the accurate phases, and the probabilistic estimate becomes accurate only if you use larger number of E values. So, when you collect the data and after converting them to normalized structure factors, they arrange it in decreasing order. They take 500 or 600 reflections only, strong E valued reflection, to generate the phase relationship. So, let us see step by step. What are the various steps involved in the 3 dimensional structure determination? Then the first one is to crystallize the compound containing the molecule, and the crystal dimension should be about 0.2 millimeter, but on all the 3 dimensions length, breadth and thickness, it should be a single crystal like a sugar crystal, you can see it, and it should not be having any crack or clustering. Then in the absence of electronic devices, those days they passed X-rays and they kept photographic film and they collected different layers, and it is complicated machinery because they do not have any device to measure the intensities, and these cameras are known as Weissenberg cameras, photographic camera. Oscillation photograph was used to detect the symmetry, and Weissenberg layer photographs have been used to collect various Bragg reflections. Now we have state of the art facilities like scanners and charge coupled devices are there, for macromolecule imaging plates are there, lab source data collection. This is the world. Just I am showing a for clarity a picture, a film after development. Each dot, the spot denotes a Bragg reflection. The camera person Weissenberg, they issue a chart so that each spot can be indexed. And how to measure the intensities? No, in the absence of densitometer, visual estimation of intensity. That is why they took 2 years to solve a structure. Now everything electron devices is automated. Whenever I talk diffraction profile, it is a profile, it will be having left background, right background. You have to subtract the background from the peak to get the net intensities. Of course, we have to apply 2 corrections called Lorentz and polarization corrections, and about which we will see separately in some of the episodes. Of course, absorption corrections should also be applied. So, these are the corrections generally needed to convert the measured intensities into the intensities which will be used for your direct methods. Now, these Bragg intensities I's are converted into normalized structure factor intensities. There is a formula is available. Once you convert everything, we do a plot, graphical means called Wilson plot. So, this will give you the overall thermal factor and scale factor. So, unless you know Wilson plot, you cannot get the scale factor and thermal factor, which is used in the calculation of E values. So, the moment you have intensities everything, then you do a Wilson plot. Average, on an average, the vibrations of each atom will be about 0.05 angstrom, 0.05 angstrom as per Shelleck's system of unit, and in angstrom square it is about 4 to 5 angstrom square. And for the reason already cited, direct method use only strong E values because they only give meaningful probabilistic relation and sharp curves. So, we select 300 to 500 strong E values to generate the triplets, 3 phase relations. So, now once you have this reflection top 500, you take the first reflection as H, second as K, then look for L in the remaining 498 reflections. We can use the symmetry operation, everything it is now automated. So, do not bother, maybe in one class, one episode we will directly do the workshop like thing, how to do this mapping, how to got the phases everything. So, now since we are going to automated program, so we are not much bothered, program does everything. So, in the generation the triplets are done, but when you take the top reflection in the beginning, we have more reflection to be scanned for the L reflection, but suppose it is a top 400 to 500, now you have come to 400th reflection, okay, from 1 to 400. So, remaining reflections are 100 only to look for L reflection such that your H plus K plus L equal to 0. The chances of finding reflection to obey this will be less. So, what I want to say is, in the beginning we have more triplets when H is in the top, and as we go down the list, the number of possible number of triplets will be less. So, that is why it is known as convergent. So, it goes like this, like convergence, larger area, lesser area. But if you look at the bottom of the convergence map, that shows reflections which are common to many things. When H is in the top, K is in the middle, or H is in the middle, these reflections are called well linked reflections. So, now after doing this convergence map, then you do one thing known as divergence map. You select the bottom reflections and assume the phases to be known, right. If you know the phase of 2 reflections, phase of the third reflection can be found. So, these are all the tutorials. One day we are going to do it here, and this is known as divergence. From a small set of reflections we are going to extend it to a large set, that is known as divergence. Okay. Now, if you have a centrosymmetric case system, there is a relation sin of H reflection and sin of k reflection should be nearly, because probability nothing is exact, nearly equal to sin of H plus k reflection. Or if you have non-centrosymmetric case, phase of H reflection plus phase of k reflection will be nearly equal to phase of H plus k. For this and this we are having separate session on how to arrive at signs of reflection or phases of reflection starting from a small set of numbers. So, this is known as divergence map. For this we have to have a concept like origin defining reflections, everything that we will see later. So, now, divergence map assumes a small set of reflections which occur in maximum triplets, phases are assigned to them using the phase relationships, unknown phases can be found for the new reflections. Okay. So, slowly we get the phases of new reflection. So, this is why known as divergence map. Okay. Now, for depending upon number of reflections you choose for the start for origin definition, you assume the phases are known or signs of reflections are known if it is centrosymmetric. If you take your pi reflection, each is having choice of positive or negative sign, we have 2 power pi starting phase sets. So, this is why I am telling you that direct methods are multiple solutions in nature. Depending upon each set of these 5 reflections signs, we have rest of the 495 reflection signs coming out. Depending upon the choice of these 5 phases, the remaining 495 reflection phases are going to come. Multiple sets are there to define the origin reflections. So, I am just giving one example. Whenever a reflection is having a 0 in it in the HKL, that reflection can have only phases 0 or pi. But when you invert the reflection, that will also having value 0 or pi only. To avoid that, so you take some more reflections and assign a value plus or minus pi by 2. So, this is known as enuntium or fixation. This also we will see later. Okay. Now, we know because multiple choices are there for origin dependent reflection, the solutions we get also are called multiple solution, from which the best solution can be picked up by a parameter known as combined figure of merit. And should it have the largest value or smallest value, it depends on which package you use. If you use Multan program, combined figure of merit, whichever set has the largest value for this, that is the best set. But in the suite of program called Shellux, yes, whichever set has the lowest combined figure of merit, that is the best one. Only for that E map is calculated. So, this table also we are going to learn in another lecture series. There are 8 types of parity in the reflection. E means even parity, O means odd. This is HKL, H even, K even, L even, H odd, K even, L even. This is how you would read. There are 8 choices of origin. So, this table tells you how the signs you assume changes when the origin is shifted from one to another, right. So, this again in depth you will see later, don't confuse now. Let us go to the program. Shellux S, S means structure determination, this is used to determine the structure using direct methods, and Shellux L is used to adjust the thermal positions after assigning them uniform value. Then our atomic positions also are adjusted, that L is known as least squares refinement. This adjustment is known as mathematically least squares refinement. Then we have a plotting program, graphic program written by Johnson from Oak Ridge University in Tennessee, okay, Oak Ridge Lab in Tennessee, USA. He called this program as Oak Ridge Thermal Ellipsoidal Plot. Your molecule is drawn with spheres, each atom is represented as spheres, and the volume of the sphere denotes the amount of thermal vibration. All these programs are packed in a package called WinGX, which is distributed by some firm. We can write it and get it freely and install in your computer. Now, let us go to the practical way of determining 3-dimensional structure determination of small molecules. Once you have collected data in a diffractometer, you have two files with you. One is known as, you can give any name, star.hkl. This is known as Bragg intensities file. We have HKL intensity standard deviation. Then another file, same name you should have, that is called .in has been instruction file. This instruction file I am going to show you next. This contains details about the unit cell dimension ABC in angstrom unit, alpha, beta, gamma and degrees. In the unit cell how many molecules are there and everything. Okay. Then it will also tell what are the scattering factor elements here, carbon, hydrogen, nitrogen, oxygen. Then in the unit cell, the same order you have to tell how many of carbons are there, hydrogens are there, oxygens are there, nitrogens are there. TREF means tangent refinement, which means that we are going to invoke the program to use direct methods. Why I am telling direct methods? There is, you know, as already there is another method known as Patterson. If you want to use Patterson, just give the command PATT, right. So, if you have amongst the 30 or 40 light atoms, one heavy atom like chlorine or bromine, you can get the position of chlorine or bromine by doing a Patterson. Then the what type of refractions are there, your data HKL F4 means if refraction contains HKL Miller indices, intensities, standard deviation intensities. If it is HKL structure factor amplitude mod f, sigma of mod f, this should be 3. Usually they give it in this format, because the program expects this way better. Now, I am showing you two files. The first file is known as .ins file, title is given, you can give the compound name or space group, everything. Cell, everything starts with 4 letters only. Cell, first parameter, what is the wavelength you are using, molybdenum. A, unit cell dimension A, B, C in angstrom unit, alpha, beta, gamma in degrees. Do not read it as Z, Z, R. Z means how many molecules are there in the unit cell. R means standard deviation A, B, C and alpha, beta, gamma. Lattice type, if it is centrosymmetric, no sign. If it is non-centrosymmetric, put a negative sign. And there are 4 types of lattices: primitive, body centered, base centered, face centered. Accordingly, the number will change. One means primitive. Then the scattering factors C, H, O, whatever you want to give, N also, if there is a, give N. Unit means in the unit cell how many carbons are there, how many hydrogens are there, how many oxygens are there. You have freedom to put oxygen first, no problem, but the 6 should come first, otherwise your structure factor, calculated structure factor should be calculated wrongly. TREF already we know, tangent refinement, which means that we are going to use direct methods. This is your intensity data, indicates end of the data. So, this is called second file .hkl file. So, we are using 2 files only. The program gives you as output 2 files. One is known as .res file and another is full detail known as LSC files. So, we are running the program called shellXS 97. It takes less than 5 seconds. EMAP is printed, everything is given here. So, finally, the program lists the last column, look, this is electron densities sorted in decreasing order, right. So, this is a 20 atom structure. Beyond 20, we just see the difference in previous electron density, other density will be more. We can cut it off and view the molecule, everything we will see in depth later. Okay. Now, LSC is there, RE is there, then finally it gives a molecule. There is a program called Platon to view the molecule, the everything structure, and Minjix should contain all the programs. Then thermal factor we are giving, you are assuming initially the vibration is same in all directions, that is an isotropic vibration. Then you assume ellipsoidal vibration 6 directions, that is called anisotropic. Then you can geometrically fix the hydrogen. Then R factor is the, what is the disagreement between the calculated observed structure factors, and that should be about 4 to 5%, which means agreement is 95% to 96%. So, these are all done automatically by yourself. Every stage you have to do isotropic, anisotropic, then every time R factor is called, then there is a parameter called goodness of fit. So, that should be closer to 1. once the refinement is completed, the mean shift by ESD should be close to 0. We talk about least square, how many cycles you want to give refinement, how many atoms you want to find extra, how many peaks you want to find, hydrogen fixing, everything is done, everything is automatic. One day we will just run the program, I will show you the results, everything. Program will give 2 R factors, but do not bother about WR2, it will be thrice the normal value, we just bother about only the conventional R value. So, this program is a compact program, and once the output is given instruction file, there is a program called parsed, written by Professor Nardelli from Italy, it will calculate inter and intramolecular features. So, in summary, we learned there is a program, automation program, which uses the measured intensities and uses direct methods to arrive at the molecular structure, and these are the references connected with this. So, this is about the automatic program for solving molecular structures. Thanks for listening.